Hello everyone, welcome back to another lesson in strength of materials, and in this video we will learn thermal effect on axial deformation. Okay, so we will be learning the deformation of a bar that is actually loaded due to high temperature or due to change in the temperature. Now, if our material is being exposed to heat or high temperature, and this change in temperature produce expansion, okay, if of course, if we have high temperature, our bar or our material would expand, and if we have a low temperature, it would contract, no? And then it would result to thermal strain and thermal stresses. A thermal strain, that is the proportional to the change in temperature, and with the coefficient, thermal coefficient, that is in terms of alpha, and our thermal coefficient here, or a coefficient of thermal expansion, has a unit of 1 per Kelvin or per degree Celsius. Okay, that's alpha. That's coefficient of thermal expansion. Then the thermal stress, we just have a stress is equal to just the modulus of elasticity times the strain, correct? That is our stress. And the value of strain, that is alpha times the change in temperature. So it's the unit of thermal stress. Now for the deformation due to change in temperature, we have the coefficient of thermal expansion times the change in temperature times the original length. Our change in temperature here, that is equivalent to the change in temperature is equal to the final or the observed temperature minus the standard temperature. Now our standard temperature is when we have length or the original length. Okay? And if our rebar is being subjected by both axial load and thermal, and at the same time it is being exposed to high temperature, so due to axial load P, it would have a axial deformation, okay? And that axial deformation here is given as PL over AE, okay? However, when we have a temperature change, okay, so what would happen is that there would be an additional deformation, and that is the deformation due to the change in temperature. So we add the thermal coefficient, the change in temperature, times the length of our structure. So this would be our total deformation. Let's try to compute problem. We have to calculate the increase in stress for each segment of the compound bar shown in the figure if the temperature increases by 100 degree Fahrenheit. Assume that the supports are unyielding and that the bar is suitably braced against buckling. So we have this bar here that is restrained at both ends, and we have this specification for this aluminum here. We have the area is 2 square inch, the modulus of elasticity, that is 10 times 10 raised to the 6 pound per square inch, and the coefficient of thermal expansion, that is 12.8 times 10 raised to negative 6 per degree Fahrenheit. And we have for the steel here, that is the area is 1.5 square inch, the modulus of elasticity, that is 29 times 10 raised to the 6 psi, and the coefficient of expansion, that is 6.5 times 10 raised to negative 6 per degree Fahrenheit. So our goal here is to compute the increase in stress, okay, that is for each segment, aluminum and steel, if we have the increase in temperature, that is 100 degree Fahrenheit. So we have, okay, so due to the change in temperature, let's say due to high temperature, so our aluminum and steel bars would have an expansion, correct? However, from the problem, our bar is suitably braced against buckling, okay, and at the same time, our bars are restrained at both ends. So these are restrained and they are braced against buckling. So therefore, there will be no deformation in our both length. Okay? So therefore, at this point here, this point B, will remain at its position. There will be no movement of B to any directions. Okay? Neither to the left side nor to the right. Okay? So, the length of both bars, aluminum and steel, are the same even though that they are exposed to heat. Okay? However, due to heat or due to temperature, there would be stress, no, in each bar. Okay? Now, if we try to draw the expansion, no, of our bar, imagining that we are having no support at this point, so we are letting our aluminum bar to expand freely. Let's say this one. Let this be the imaginary expansion of our bar. Let this as the change in the length of the bar due to the temperature. Okay, that's for aluminum. The same as with the steel. If we let our steel to expand freely, so most probably this would be the expansion. Okay, and let this be the deformation of our steel bar due to the change in temperature. Okay, now take note, since these bars are expanding and not moving at the same time, so we could say that there is a resisting force P here that is acting opposite to the direction of the expansion. Okay, and that force P, let this be the force acting on steel, and this one is the force acting on the aluminum. So these actual loads here are responsible why we do not have deformation on each bar. Okay, so therefore they counteracts opposite in the direction of the expansion, so that again our point B here will remain at this point. There will be no movement. Okay, so therefore let us take this as our deformation or the actual deformation of the steel, and this one the actual deformation of the aluminum. Okay, so we can create a relationship of the steel here, the temperature and the actual deformation, by summing up, since we know that this total deformation of temperature here is equal to the deformation due to the actual load P. Okay, so therefore we could say that due to the temperature, deformation due to temperature is equal to the deformation due to actual load. Now, our temperature here is we have the deformation of the steel due to temperature plus the deformation of the aluminum due to temperature is equal to the actual deformation of our steel plus the actual deformation of our aluminum. Okay? So from the formula of thermal deformation, we have the coefficient of thermal expansion times the change in temperature times the length of our bar. So let's start with steel. Okay, so our steel here is equal to, now we know that the coefficient of thermal expansion of steel is equal to 6.5 times 10 raised to negative 6 degree Fahrenheit. The area is 1.5 square inch and the modulus of elasticity is 29 times 10 raised to the 6. We have 6.5 times 10 raised to negative 6. This is in terms of degree Fahrenheit, diba? Okay. Times the change in temperature, we have the degree Fahrenheit, 100 degree Fahrenheit, times the length of our bar, that is in 15 inches. So we can cancel out degree Fahrenheit, the remaining would be in inches. Correct? So the answer is equal to 9.75 times 10 raised to negative 3 inch. Okay? Now for aluminum, we have the thermal expansion, that is 12.8 times 10 raised to negative 6 times the change in temperature is 100 times the length of our aluminum, that is 10 inches, and this equals to 0.0128, that is in inch. Okay, since we need to add these two, the thermal deformation of steel plus the thermal deformation of aluminum, and if you add these two, we have 0.02255. That is the total thermal deformation. Okay, so we use at this compatibility equation. By using this compatibility equation, we could have 0.0225, okay, is equal to, now the actual deformation in our steel, so that is this one, that is we have the load PS, okay, the actual load PS, that's unknown, times the length of the steel, that is 15 inches, over the area of our steel, that is 1.5, times the modulus of elasticity of our steel, that is 29, times 10 raised to the 6, plus the actual deformation in aluminum, okay, that is we have this one, that is PA, times the length of aluminum, that is 10 inches, over the area 2, times 10, that is the modulus of elasticity, raised to the 6. Now take note, since at this point B, we have our force that is in equilibrium at this point, so therefore we could say that our PS is equal to PA, since they are in equilibrium. The summation of all our force at point B should be equal to 0. Okay, so therefore that is equal to P. So let this be our P. Then by further simplifying, we could have of the value of P, that is equal to 26,691, that is in pound. So therefore this is the actual load P that is acting opposite to the expansion of each bar. Okay, now since the problem asks for the stresses in each bar, so we need to compute the normal stress. So therefore we have the normal stress for steel. Let's try to compute for steel. We have P over A, correct? And this is 26,691, that is pounds, over the area of the steel, that is 1.5 square inch. Then we have 17,794.558. Okay, that is in PSI. So this is now the stress, okay, of steel. Now for the stress in aluminum, we have 26,691 over 2, that is in pound square inch. So we have 13,345.918 PSI. So this is the stress in aluminum. I have here a new example, this one. After a load P that is equal to 150 kilonewton is applied to the pin-connected structure shown, the temperature increases by 100 degrees Celsius. The thermal coefficients of expansion are 22 times 10 raised to negative 6 per degree Celsius for the aluminum rod A. So let's tabulate this one rod A, that's aluminum. The thermal coefficient of expansion, that is 22 times 10 raised to negative 6 per degree Celsius. And for steel rod B, this one is steel, that is the coefficient of thermal expansion is 12 times 10 raised to negative 6 per degree Celsius. And the modulus of elasticity of aluminum is 75 gigapascal. And for steel, of course, that is 200 gigapascal, respectively. The cross-sectional area of members A and B are 100 square millimeter and 500 square millimeter, respectively. So we have aluminum, the area is 1,000 square millimeter, and for the steel, that is 500 square millimeter. Now, if member C and D is rigid, Determine the normal stress in bars A and B. So we are asked to compute for the normal stress for A and B. Now, since we are looking for the perpendicular stress, so therefore we need to compute its axial force, or the axial force in each members A and B. Okay? So we could create an equation by summing up or summation of moment with respect to any point. We have this one that is, if we have 150 kilonewton that is acting at D, so it would create a reaction at bar B and bar A. Okay, so these are the axial forces in the both bars. Now take note, at point C we have pinned here, so therefore it should have a vertical reaction. If we sum up forces vertically, we could have three unknown forces in this one, since we have vertical force or vertical reaction at point C. So therefore, our number of unknowns would exceed the number of equations, since we only have two equations that could create in this one, that is summation of forces vertical or summation of moment. But since, again, we cannot include, or we cannot use summation of force vertical, so we could only have summation of moment, let's say at point C, so that our reaction at point C will not be included. So we have summation of moment at C is equal to 0, counterclockwise or positive, then we have 1.5 PB plus 1.5 plus 2.5, that is 4 PA, is equal to, let's convert it into Newton. Okay, since eventually we will be converting all of this into Newton. So let's say that's 150,000 times the moment arm from C, that is 5. Okay, so we have, let's arrange it in alphabetically. We have 4 PA plus 1.5 PB is equal to 750,000. So this is our equation number 1. Okay? So how are we going to create our equation number 2 in this problem? Again, we cannot sum up forces vertically since we have a reaction at C, vertical reaction at C. So we need to come up with a compatibility equation by just looking at this deformation here. Okay, now we know if we have our load 150 kilonewton, since our bar is rigid, it would deform like this one. Okay, so we have this deformation of D, that's the vertical movement of D. This is the vertical movement of our point A, or this one is the elongation of our bar A, and this also the elongation of our bar B, which also the movement of our point B here. Okay, so how are we going to create a compatibility equation? Now we know that this is just similar triangle, correct? Now we could create a relationship of our two deformations A and B with respect to their respective distance from point C. So we could say by ratio and proportion, that is equal to the deformation at A is over 4 is equal to the deformation at B over 1.5. Or we could say that deformation of A is equal to 4 over 1.5 the deformation of B. Okay? So we can further simplify it like this one. Deformation of A is equal to 4 divided by 1.5. That is equal to 2.667 the deformation of B, bar B. Okay, so we have this our compatibility equation. But we can further simplify it, this one, since we know our deformation of A is equal to the, since we have the combination of the deformation of our axial due to axial load plus the deformation due to change in temperature. Okay, so we can substitute this in our compatibility equation. So we could say that our deformation at A is equal to the deformation due to axial load at A plus the deformation due to the change in temperature at A is equal to 2.667 times The same as with the deformation at B, it is still combination of the actual load deformation at B plus the change in temperature at B. So we have here the deformation due to actual load at B plus the deformation due to the change in temperature at B. So this is our simplest form for our compatibility equation. Then let's substitute all the formula for every deformation, and we know that our actual deformation is equal to PL over AE, and the change in length due to temperature is equal to the coefficient of thermal expansion times the change in temperature times the original length. So therefore, using this formula, we could further express this in terms of actual load. That is, let's start from the deformation due to actual load. Let's say that is the actual load at A. We have PA times the length of A. Now we know that our length of aluminum, that is 2 meters, okay, that's A bar A, that's 2,000, that is the longitudinal length of our bar. 2,000 over the area of our aluminum, that is in 1,000 square millimeter, okay, times the modulus of elasticity, that is 75, then times 10 raised to the 3, so that we could have unit here, that is in terms of Newton per square millimeter. Here is square millimeter, then we have a millimeter here, and the remaining unit would be in terms of millimeter over Newton, which will be simplified it further once we substitute the deformation due to temperature. So then we have the deformation due to change in temperature, that is using this formula here, and we have the thermal or the coefficient of thermal expansion, that is 22 times 10 raised to negative 6. This is the thermal expansion or coefficient of thermal expansion for our aluminum, times, this is in terms of degrees Celsius, okay, then times the change in temperature. Since our temperature increases 100 degrees Celsius, so we have 100 degrees Celsius, that is the change in temperature, times the length of our aluminum bar, that is 2,000, okay, that is in millimeter. So we can cancel out here the degrees Celsius, correct? And so the remaining would be millimeter here. So that is in terms of, that is the unit of deformation for our change in temperature. Let's continue. We have equals 2.667 times, we have the deformation due to actual load at B, that is, let's say that's PB, since PB is unknown, times the length of our bar B, that is 1.5 meters, or that is 1,500. 1,500 over the area, that is 500 square millimeter, times the modulus of elasticity, that is 200 times 10 raised to the 3, okay, plus the deformation due to temperature, that is we have the coefficient of thermal expansion of our bar B, or for the steel, that is we have here 12 times 10 raised to negative 6 per degree Celsius, 12 times 10 raised to negative 6 times the change in temperature, that is 100 degrees Celsius, then times the length, that is 1,500. Okay, so we can further simplify this equation. We could have 2.667 times 10 raised to negative 5, that is in terms of PA, plus we have 4.4, okay, is equal to, we distribute 2.667 inside the parenthesis, okay, then we evaluate this first term, then multiply the value by 2.667, then we could have 4 times 10 raised to negative 5, that is PB, plus evaluate this term, then multiply the value by 2.67, then we could get 4.8. So rearranging our equation, we could have 2.67 times 10 raised to negative 5 PA minus 4 times 10 raised to negative 5 PB is equal to 4.8 minus 4.4 gives us 0.8 4. Okay? And this one is our equation number 2. Since we have already completed the required number of equations, we have equation number 1, equation number 2, we can now perform simultaneous equation to determine the value of PA and PB. Okay? So you can use by elimination method or by substitution method. But I'm gonna teach you to use your calculator. So you just need to click mode, the number 5, the number 1, then encode the coefficients. Okay, 2.67 times 10 raised to negative 5. Okay, then equals, that is negative 4 times 10 raised to negative 5. And the value on the right side, that is 0.4. That is for the first or the second equation. Now for the first equation, we have 4 is 1.5. Okay, then 750,000. And we have this value 152,996.175, that is in terms of Newton. And we have 92,010.2 Newton. We have our PA, that is 152,996.175, that is in Newton, or we could say that is 153 kilonewton. Okay, we can round it up. Now for PB, we have 92,010.2, that is in Newton. So therefore, we could say that it is 92.01 kilonewton. Okay? So our goal here, of course, is to compute for the stress. It's letter A. So we have, for the stress on bar A, we have P over the area. That is, now the PA, the actual force at A, that is 152,996.175 Newton over the area of A, that is 1,000 square millimeter. The answer, 153, that is in megapascal. Okay? So therefore, this is the stress in the aluminum due to the axial load, okay, and the change in temperature. Now for the stress experienced by steel or by bar B, we have PB over the area of our B, that is we have 92,010.2 Newton over the area, that is 500 square millimeter. So we have the stress 184.02 megapascal. So this is the stress experienced by the steel. And these are our final answer for letter A question. Now for letter B, we have the vertical component of the displacement of point D. So we are asked to compute for the value of D here. This one. That is the vertical displacement of our point D. And we can do it by just ratio and proportion. We have the relationship, that is the deformation or vertical displacement at D over the distance from C, that is 5, is equal to, we could use either deformation at A or at B. Okay, so let's use deformation at A over the distance from C, that is 4. Okay, so therefore, we have the relationship that the deformation at D is equal to 5 over 4 of the deformation at A. So we are going to use this compatibility equation. And then we know that the deformation of bar A is equal to the deformation due to actual load P plus the deformation due to the change in temperature. Okay? Now let's compute first the deformation of A, that is equal to, we know that our deformation due to actual load, that is P L over AE of our aluminum plus the change in temperature, that is the coefficient of thermal expansion of A, then the change of temperature times its length. So let's substitute everything in this equation. Now we know that our actual load, we have already computed this one, that is 152 times 996.175 times the length of A, that is equal to 2,000, okay, over the area, that is 2,000 square millimeter, times the modulus of elasticity, that is 75, times 10 raised to the 3. Okay, we raise it to the 3 so that we could have a Newton per square millimeter unit. Plus the thermal coefficient. We know the coefficient is 22 times 10 raised to negative 6 times the change in temperature, that is 100, times the length here, that is equal to 2,000. So we could have the value of the total deformation of our bar A, that is equal to 8.48 millimeters. Now we use this value of our total deformation of A to this compatibility equations. So therefore, we could have the vertical displacement of D is equal to 5 over 4 times, we have 8.48 is equal to 10.6 millimeters. So this is the vertical displacement of D. Okay, so therefore we have 10.6 millimeter vertical displacement of point D. So this is our answer, question letter B. And that ends our second example. So let's try to solve another one. We have